Welcome friends, Igor is here, and in this video we will discover 10 properties of vector operations that we will eventually use to define abstract vector spaces. So, in this lesson we will discover 10 properties that the operations of vector addition and scalar multiplication satisfy, and we will prove that indeed the vector operations satisfy these properties. Let's get started. I will call the list of 10 properties we are about to discover the vector space properties. This is because column vectors are not the only objects that satisfy these properties, as we will soon discover, and these properties will be a basis for our definition of an abstract vector space. The first property says that the vector space of column vectors of size m is closed under the operation of vector addition. Namely, if you add two column vectors of size m, the result is another column vector of size m. That is, by performing the operation of vector addition, you always stay inside the set Cm. This is the closure property. The second property says that the vector space Cm is also closed with respect to the operation of scalar multiplication. The third property says that the operation of vector addition is commutative. The fourth property says that the operation of vector addition is associative. This is in fact a very important property for every binary operation, because it says that no matter how many vectors you're going to add, it doesn't matter how you use the parentheses to break this operation in pairs. Why do you need to break the operation of vector addition in pairs? It's because the operation of vector addition is a binary operation. You can only add two vectors at a time. You cannot add simultaneously 3 or 4 or 5 vectors. This is not how the operation was defined. The fifth property says that there is a special vector called the zero vector, which serves as a neutral element with respect to the operation of the addition of vectors. If you add this zero vector to any vector u, then you will not have changed the original vector u. Property 6 says that for each vector there is an additive inverse. Namely, for each vector u, there is a vector which we denote by negative u, which has a property that vector u plus vector negative u is equal to the zero vector which was defined in the previous property. Property 7 says that the operation of scalar multiplication is associative. If you scale a vector u by a scalar beta and you obtain a new vector, and then you scale that new vector by another scalar alpha, this is the same as if you simply multiplied the two scalars as numbers and performed one single scalar multiplication operation. Property 8 says that scalar multiplication distributes over vector addition. Property 9 is another version of the distributive property, except now, on the left-hand side, we have the addition of scalars, while on the right-hand side, we have the addition of vectors. Keep in mind, we have two plus signs, but they are different operations. On the left, it's the operation of the addition of numbers. On the right, it's the operation of the addition of vectors. Property 10 says if you scale any vector by scalar 1, then this is the same as the original vector. It may seem obvious why even bother stating this property, but we will see later that this is a very important property to keep in mind. Now that I stated all these 10 properties, let me convince you that in fact the vector operations do satisfy all these 10 properties, and I will prove each such property one at a time. First, let's prove that the vector space of column vectors of size m is closed under the operation of vector addition. This property should be obvious from the way we defined the operation of addition. We add two column vectors of the same size, and the result is a new vector which has the same size as the two original vectors. Let's prove that the vector space of column vectors of size m is closed under the operation of scalar multiplication. This is also clear from the way we defined the operation of scalar multiplication, because if we scale a vector of size m, it is again a vector of size m. Let's prove that the operation of vector addition is commutative. Let's pause for a moment and spell out what it is that we need to prove. We need to prove the equality of two vectors, and we know that to prove two vectors are equal, we simply need to show they have identical components. This helps us figure out how to proceed. I'm going to take an arbitrary component number I of the vector u plus v, and I will prove that it is the same as component number I of the vector v plus u. So let's start with component I of vector u plus v. By the definition of the operation of vector addition, this component is equal to component I of vector u plus component I of vector v. But what we have now is a familiar operation. This is the addition of two complex numbers, and we already know that addition of numbers is a commutative operation. Therefore, when we add two numbers, ui plus vi, this is the same as vi plus ui. And now all we need to do is to make the backwards translation. Vi plus ui is in fact component number I of the vector v plus u. This proves that the vectors u plus v and v plus u have identical components, and therefore they are equal as vectors. Let's prove that the operation of vector addition is associative. Once again, to do this, we will show that the two vectors have identical components. I'm going to start with an arbitrary component I of the vector on the left-hand side of the desired equality. We are going to use the definition of the operation of vector addition to understand what this component looks like. What we have is vector u plus the vector v plus w, and therefore the ith component of this vector is component I of vector u plus component I of vector v plus w. Component I of vector u is ui, and component I of vector v plus w is vi plus wi. This is again using the definition of vector addition. And now we arrived to a familiar situation. We have an operation of addition on numbers because the components of vectors are simply complex numbers. We do know that the operation of addition of numbers is associative. And now all we need to do is to translate this back in terms of the components of the vectors. So what we have is component number I of vector u plus v plus component number I of vector w. By definition of the vector addition, this is component I of vector u plus v plus the vector w. We have proved that the two vectors have identical components and therefore they are the same vector. From this proof, you see that the fact that the operation of vectors is associative is a simple consequence of the fact that the operation of addition of numbers is associative. Let's prove that there exists a vector called the zero vector, which works as a neutral element for the operation of the addition of vectors. Now, this is obvious, and we already defined this zero vector previously. If you take a column vector, all of whose components are equal to 0, this is exactly the vector you're looking for. So, this zero vector has the same property with respect to the operation of addition of vectors as zero number with respect to the operation of addition of numbers. They both are neutral elements with respect to these operations. Let's prove that each vector has an additive inverse. Given a vector u with components u1, u2 through un, what do you think is the negative inverse? Well, it's kind of obvious. You simply negate each of the components, and it's clear. When you add this new vector to the vector u, what you will get is the zero vector. Let's prove that the operation of scalar multiplication is associative. To prove the equality of two vectors, I will show that they have the same components. So let's start with component I of the vector on the left-hand side. By the definition of the operation of scalar multiplication, this component is equal to scalar alpha times the ith component of the vector beta u. But the vector beta u is a scalar multiple, so let's use the definition of the scalar multiplication one more time. The ith component of the vector beta u is beta times the ith component of u, and therefore our ith component can be written as alpha times beta ui. What we have now is multiplication of three numbers, and we do know that the operation of multiplication of complex numbers is associative. Now let's translate this expression in terms of the components of the vectors. We have a scalar alpha beta multiplied by the ith component of the vector u. By the definition of the scalar multiplication operation, this is the same as component I of the vector alpha beta times u. This proves that the two vectors have identical components and therefore they're equal as vectors. Also notice that this proof was based on the fact that multiplication of complex numbers is associative. Let's prove the distributive property for vector addition. Once again, I will do this by showing that the two vectors have identical components. The component I of vector on the left-hand side is alpha times component I of the vector u plus v. Here I'm using the definition of scalar multiplication. Now let's use the definition of the vector addition. Component I of vector u plus v is component I of vector u plus component I of vector v. Now we have an expression that involves numbers, and we know that for numbers, multiplication distributes over addition, and therefore we can write this. Next, let's translate this number in terms of the component of a certain vector. First of all, we observe that by the definition of the operation of scalar multiplication, this is the ith component of the vector alpha u plus the ith component of the vector alpha v. Also, by the definition of the operation of vector addition, this is the ith component of the vector alpha u plus alpha v. This shows that the two vectors have identical components and therefore they're equal as vectors. Notice that the proof of this distributive property for vector operations was based on the distributive property of the corresponding operations for numbers. Let's prove that addition of scalars distributes over scalar multiplication into the addition of vectors. The ith component of the vector on the left-hand side is equal to alpha plus beta times the ith component of u. This is the definition of the operation of scalar multiplication. But now we have numbers, and we know that for numbers multiplication distributes over addition. Using the definition of the operation of scalar multiplication in the other direction, we see that this is component I of the vector alpha u plus component I of the vector beta u. Using the definition of the operation of vector addition, we see that this is component I of the vector alpha u plus beta u. This shows that the two vectors have identical components and therefore they're equal as vectors. Once again, to prove this version of the distributive property, we used the distributive property of the operation of numbers. Finally, let's prove that scaling a vector by scalar 1 does not change the vector. Again, this is kind of obvious, because if you multiply each component of the vector u by number 1, you do not change the component. So this is an obvious property, and it may not be clear why it is even worth mentioning. But the reason for this will become clear later once we start talking about abstract vector spaces. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see future videos. In the next video in this series, we will discuss linear combinations of vectors and their applications to solving linear systems. I will see you later.